Hey guys, so I'm going to use this video to help you kind of power through the next couple assessments that we're going to be doing in class, but basically we're going to transition from what you've been learning in class and apply that to an actual scenario that we see in earth science in general. So we're going to shift our focus in class to productivity in the Gulf of Maine. But before we understand the productivity part, we actually have to understand how the Gulf of Maine functions as a system. So I'm going to jump right into this. First, we can do a quick review of the content we covered in class. But I kind of started you guys off with energy transfer, so this was the time lapse I had left you guys to look through. Basically, your energy source was underneath the die, and through a combination of radiation and actually a little bit of latent heat, you get that transferred into the tank, so it's an external energy source. And then through convection, because you're changing the density of the water now, you get that water to rise and then spread out across the top. And when it's moving horizontally, that's when you get the advection. Oh, and I almost forgot, the water warms from conduction right between the water and the tank. So that's kind of one scenario that involves all the energy transfers. So that's kind of an example of how a fluid responds to when you heat it from the bottom. You get convection and all the other stuff that cascades through it. On the other scenario, what we kind of jumped into after that is understanding why, say, that fluid behaves the way it does. So this is talking about how the properties of matter kind of dictate how that substance will behave under certain circumstances. So this is another time lapse that a student did a few years back, where basically they created a scenario: ice, brass weights, and Legos, and over time as the fluid heats up they all separate by density. So this would be an example of something that wasn't stratified becoming stratified over time, just based on density. We see this with fluids in general, so anytime you get a slight variation in density, those fluids will move and begin to separate based on its density, right? So what I really want to see you guys do is take these concepts that we learned in class and apply it to what's happening in the Gulf of Maine. So if you guys are not familiar with what the Gulf of Maine is, so this star represents us, and we're just off of this map. So this is looking at, we have Boston, Portsmouth, Portland, Bangor, kind of right up the East Coast here. And the Gulf of Maine is this shallow body of water right offshore for us. It's pretty much, it's actually a relatively isolated system. So if you look to the south side of it, so right over here we have George's Bank. That's referenced in a lot of old history texts about fishing and when this area was first settled. You also get Brown's Bank. So these are really, really shallow areas. And the Gulf of Maine itself, that basin, the whole basin of the Gulf, is actually pretty rugged mountainous terrain underneath the water. So it's not like it's just this shallow, flat basin of water like we see in a lot of other shallow seas. It's pretty rugged. And so to give you an idea of what that looks like, I did this cross section so we could look at it from a side view. Off to the left-hand side of the screen is basically the continent. So this is starting in, I actually put the point in Belmont and started working out towards Portsmouth. So you can see how the land just kind of tapers off, averaging about 600 to maybe upwards of 1,000 feet. And as you move down to the shore, it gets down to sea level, and there's your zero. Then you see the line drop below zero. This is the Gulf of Maine right here. So this blue area covering the green above, that green is how shallow the Gulf of Maine is. So on average, the Gulf of Maine is somewhere between 600 to maybe in the deepest parts about 1,000 feet deep. So it's actually a really shallow body of water. And then you see off to the right-hand side of the screen here, that's George's Bank. So George's Bank is even shallower than that. It's only a couple hundred feet deep. It's really, really shallow considering the size of it sitting right offshore. And then once you get beyond George's Bank, it drops right off, and that's the Atlantic Ocean. So that's the end of the continental shelf right there. So you can actually see the land mass drop off right into the water. So that's the end of the continent. And that is only about 300-ish miles from us. All right, so the end of the continent's 300 miles away. And the Gulf of Maine itself is maybe 100 to maybe 200 miles wide in that widest part. Um, so that kind of gives you an idea of what the Gulf of Maine is. So it's a very enclosed body of water right offshore of Massachusetts, Maine, New Hampshire, Nova Scotia, New Brunswick are kind of all the states and provinces surrounding it. So what's it famous for? If you've ever had the chance to visit, go to the beach, go out on a whale watch, these are some of the things that the Gulf of Maine is really well known for. So one of the biggest things, especially in the springtime, if you go out late May, early June, whale watching is kind of famous. So for example, you see a lot of finback whales. This is, I believe, the second largest whale in the world. They migrate to the Gulf of Maine to feed. You also get a lot of minke whales in the Gulf. One of the first times I ever went whale watching, I got to see minke whale breach like this just offshore of Kennebunk. You also have right whales, which is an endangered species. This is really, really rare to see these. And actually, one of the only places they're found now in the Gulf of Maine is right off of Grand Manan Island in Canada. Um, so really low population, struggling to survive, and the Gulf of Maine is one of their specialized habitats. And then probably the most famous of all the whales and the ones that are tracked the most are humpback whales, and these travel thousands of miles in a year through their migration all the way down to equatorial regions in the Caribbean and mid-Atlantic, all the way up to Arctic regions. And they go through that migration every year. So a lot of these whales follow similar migration patterns. Besides whales in the Gulf of Maine is also really famous for its fish populations. So obviously seafood in New England is famous. That's what we're known for. So you get a lot of cod, herring, mackerel, and other fish species that have sustainable populations in the Gulf that we spend a lot of time harvesting those. Um, Also, Maine lobster in general in the Gulf of Maine. This is world famous. And yes, this is an actual picture. These lobsters can sometimes be blue, which is awesome. That's really rare. Most of the time, they're that dark red, brown, rocky color. Um, yeah. So, seafood in general. So, beyond the fish and the lobster, you also get a lot of things like oysters, periwinkles, clams. There's a lot of food that's harvested out of the Gulf of Maine. So honestly, the Gulf of Maine is one of the most productive bodies of water in the world. And before we jump into understanding how it's so productive, we really have to understand how the Gulf of Maine is functioning as a system, just the water itself, right? So the last thing that it's really famous for is its tides. So here's a time lapse looking at Bay of Fundy National Park. So if you start in Portsmouth or the southern part of the Gulf of Maine, the tides generally are around 4 to 9 feet, and then as you move down east or like up the Maine coast, those tides will increase to 10, 13 feet. Once you get to Eastport and Lubec, Maine, the tides get up to about 22 feet on average, and then further up into Canada and New Brunswick, when you get the tides, on average they're above 30 feet. And in this case, I think the video said this was just over a 45-foot tide. So imagine that. That's like saying twice a day the water goes from being ground level outside the school to above the entire school and then back down. So that's a huge volume of water that gets moved daily in the Gulf of Maine. So really, really large tides, among the largest in the world. So you get those cool rock formations that happen just outside of it. All right, so when we're studying any of the earth sciences in general, we tend to track data automatically. So we log and create and build these huge data sets that then we store online. These data sets can be collected remotely, so we call it remote sensing. So that would be kind of like satellite. Um, we also collect data from boats. So a lot of boats into their hulls have sensors built into it that sense water temperature and other things about the water that they can measure. We also have a very complex buoy system all throughout, especially in the Northeast. So in the Northeast, the organization that runs it is known as Niracus. They have a whole series of buoys. I want to say I think they have over 100 buoys throughout just New England alone. But the kind of cool thing with these buoys, so they have weather stations on it. They have all kinds of instrumentation on the buoy itself, but then on the anchoring system going down into the water columns, a lot of times what they do is they actually add sensors. Um, there we go, to that. So imagine each smiley face in this case represents a specific sensor going down, and they might put the same sensor at different parts on that line. So for example, the common depths in the buoys that we're using are 11 meters, 120 meters, and 150 meters deep below the surface. Um, so that kind of gives you an idea of what we had. There are lots of data available, and we're going to use a little bit to understand what's happening in the Gulf of Maine in terms of how does energy transfer through it, and as a result of that energy transfer and changing what's happening in the water, when does the water become stratified, and how does it become stratified? Um, so I'm going to kind of exit out of this and kind of jump in. So I have two assignments for you guys in this next week in class. One of them, and they're really not overly, the hardest part is making the graphs and then interpreting the graphs. So the first one's going to focus on energy transfer, where you're basically going to look at the whole water column as a body that gets heated unevenly. So you have to try to think of where is the energy coming in? Where is the source? Is it external or internal? So when we're talking earth science, typically we use internal energy to describe energy coming from beneath earth surfaces. So like the core of the earth. That provides the majority of the internal energy. For external sources, that would be something, so you have Earth, anything that's supplying energy from outside the Earth system, we refer to as an external source. So that would be something like tidal energy from the moon or external energy from the sun. So when you produce these graphs, you actually have to think about where the energy is entering the Gulf. Is it entering at the surface? Is it entering at the bottom? And depending on where it's entering, you should be able to make a justification of where that source of energy is coming from. So really what I want you to work on is producing a graph and learning how to use that graph as evidence for an argument that you're trying to support. The second one focuses on stratification in the Gulf of Maine. So when does the Gulf become stratified? So remember when you did the water columns in class, the density columns, and you make those layers, some of those layers really separate from each other, and they're hard to mix depending on how big of a difference the density is in those columns. So what we want to do is understand whether or not that actually happens in the Gulf of Maine, because if you get a big break in density like that and the water column becomes stratified, then that water is not going to mix. And if it can't mix, that has other implications, say, depending on what that water is supplying. So for example, if water is bringing nutrients to a certain part of the water column and suddenly that supply gets cut off, then that means that whatever life needs those nutrients, it's not going to get it. So understanding how the water moves and circulates and mixes is really important to understand. Otherwise, we're not going to get what happens to life in the Gulf of Maine, or why we get these huge boosts in productivity and all these migrating whales and other organisms that come and visit the Gulf of Maine every year. So on both of these documents, let's see, yeah, so right by the data and data analysis, there's a link here that says download data. So when you do that, it'll download it. Then you can open it right up. You're going to need to be on a computer that has Excel to do these graphs. Otherwise, it gets really, really complicated really fast, and you're not going to be able to do these graphs on Google Spreadsheet. You don't have enough control. You can do basic graphs on Google Spreadsheets, but not these. So it's going to open up a spreadsheet a lot like this. So it says Gulf of Maine phytoplankton bloom data. And it's protected view. You're going to have to actually enable editing before you do anything. Couple important things to think about. Whatever you plot in a graph, whatever column is furthest to the left, actually for you it's that way. So whatever column is furthest to the left is the one that's going to be plotted on your x-axis. So if I click here, for example, on column B, and then hold down Control and hold column C, that means column B will be on my x-axis and column C will be on my y-axis. So if you go in the tabs in the bottom, this Western Main Shelf B and Central Main Shelf E are the two buoys that I pulled, and that was actually plotted on the map, I think. Wait, did I show you that slide? On one more slide, I missed that. So here's where they are. So they're both just off the shore of Maine. One's kind of in between Portsmouth and Biddeford over here, so just offshore Kittery. And the other one is just offshore south of Rockland and kind of east of Portland, right? So that's both of those buoys. So we'll come back here. So if you come to this, you have access to both of those. You can work out of either one. Actually, in looking at this now, there's an error in Central Main Shelf E. So use the B shelf, otherwise your graphs won't work out. There's going to be an issue. So for example, if I wanted to compare the effect that water temperature had on salinity, because I am saying water temperature would be my independent variable, I would want that on my x. I can't just highlight the 11-meter water temperature and the 11-meter salinity and make a graph, because the axis will be reversed from what I want. So what I would actually have to do to make those graphs that way is move my salinity over to one side, highlight the two columns I want, I'll hold down Control, and now I can actually create a graph that compares these two variables against each other. To make a graph, super easy, highlight what you want for data, go up to Insert, we do XY scatters. If it's a time series, you can actually do the straight line, the ones right here where you're actually connecting it. This is not a time series though. If it's not a time series, meaning you're plotting something like temperature and salinity against each other for some reason, then you would want to just do the one with the dots with no connecting lines. The order that these dots are in does not matter. So you get a basic graph like this. Right away, you're going to want to add axis titles. You're going to want to name all those. You can add a legend. You can also, anything you want to manipulate in the graph, you basically right click on it. So I have a lot of white space off the edge of this graph. So I'm actually going to right click on the 20 and I can go to Format Axis. And if I wanted to say, instead of starting at 0, start at a temperature of 20 degrees Fahrenheit, then I could just change my minimum value for my x-axis to 20. All right. Anything you want to change for titles, so let's say I wanted to say this was temperature, always include your units. All right, and then I'll hit enter and that'll change it. So that's temperature in degrees Fahrenheit, and then I did salinity in PSU. Alright, so I have both variables names, I have the units in there, and then I would officially change this. Your titles of your graphs should also always describe what the graph is plotting, right? So this is basically the effect water temperature has on salinity. right? And then I would put Gulf of Maine, and usually you add some sort of date range. So when someone reads your graph, they want to know where the data came from, what's being plotted on the graph, and when these data were collected, right? So it's a little extra effort. If you have, I have another video that I made a while back that kind of explains scatter plots in general, but that's something you can add to or change there are examples there of what you can do with your titles, right? One last thing, if I wanted to add other depths to this, you have to actually manually add data sometimes. So for example, I'm going to compare other depths in here to see if the same thing is happening between other layers too. So this is only that 11-meter depth. So this is right up by the surface of the water. So if I wanted to see if the same thing happened at other depths, for example, I'm going to add the 120 meters, so you just kind of follow along, right? So I right-clicked on the graph, I selected data, and then I'm going to add a new series. The series name is going to be 120 meters now. My X values are going to be the 120 meter temperatures. You can't include the title when you add them in this way, so I can't just click on L and call it good. So I'm going to click on that first 42.4, and then I'm going to go all the way down to the bottom, hold shift, and then I'm basically going to do the same thing, except you have to delete what's already in there for Y values, and then you can just start from the bottom. So that 32.09, come all the way up to the top, hold shift, 32.7, hit OK. It adds in that second series. So you can also add other things in here. I'll hit OK, I'll just leave that. So you can keep going until you add all three. If you right click on any of the dots on here, you can add a trend line. This is really kind of useful for looking at strengths between relationships or assessing a relationship. So all it's doing is it's adding a line of best fit in here. Always assume it's linear unless it's really apparent and obvious that the relationship is non-linear, right? So in this case, this appears to be a linear relationship. And then the last thing you can add is an r-squared value, right? So I'm going to kind of adjust this. The lines get color-coded anyway, so if you wanted to delete where it says a linear 11 meter, I'm going to click on my legend and then click on linear 11 meter and then hit delete. And that moves it over. And I can just put this r-squared value right there. If you don't know how to read an r-squared value, actually I'll put this one above the blue. So an r-squared value is a value that's between a number between 0 and 1. 1 means that basically your independent variable explains 100% of the variance in your dependent variable, right? If it was 0, it would explain 0% of the variability in your dependent variable. So in this case, what this is saying is water temperature explains about 60% of the variability in salinity. So that's not, it's hinting that there might be a relationship there, but that's not an overly high r-squared value. So typically, when it starts getting upwards of 0.7 to 0.8, that's when you really start being able to make claims confidently that a relationship is really strong or exists between variables. It does not necessarily mean that one is causing a change in the other, but it's hinting that there is some sort of relationship that exists, and you could come up with or find an explanation as to why that relationship possibly exists. So we can kind of do the same thing with the red. I'm going to add a trend line here. We'll add the r-squared. I'll pull that down here. And then I'll delete this again. Here we go. Alright, and we notice that the r-squared value dropped. Who knows? It could have dropped for a bunch of reasons. You're going to notice that the deeper depth, the one that's further below the surface, there's not as much of a variability in temperature. And maybe because of that alone, because if you look at the graphs, they kind of overlay each other perfectly. So The fact that the R² value is dropping is implying that they're just, maybe because there's a lower range in temperature at that deeper depth, it's not going to explain or be as strong of a relationship. It's hard to say sometimes depending on what you get for R² values, but anything you see that's above 0.7, you can start to say, yeah, this relationship exists and this makes sense. Um, Anything above zero point 0.9 or 0.95, it's a really, really strong relationship. So usually if you get something like that, you can confidently say, oh yeah, temperature affects water in this way, and here's how I know, and here's why this happens, right? So that's kind of the goal of these labs, is for you to be able to produce graphs and then use those graphs to help support whatever argument you're trying to make in the lab, right? So you have the week, work through these. If you have any questions on how to make graphs, I would pull up videos on YouTube. My videos maybe tend to be on the boring side. You don't even have to use my videos. Depending on who's in for a sub or other teachers that are available to you, you can also use them as a resource if they're comfortable with Excel. Or like I said, just send me an email and I'll happily help you. Alright guys, so I'll set this up and you'll be able to access this all through Google Classroom, obviously. Alright, bye guys.